If you zoom in far enough on the universe, you might expect to find the ultimate, infinitely divisible building blocks of reality. You start with living cells, slide past complex molecules, dive deep into atoms, and split apart subatomic particles like quarks and electrons. For centuries, classical physics assumed you could keep slicing space into smaller and smaller pieces forever. It imagined space as a smooth, continuous fabric, infinitely stretchable and infinitely smooth. But modern physics has uncovered a staggering possibility. Space may not be smooth, and it cannot be divided forever. There appears to be a fundamental flaw to reality, a smallest possible unit of distance beyond which the very concept of space dissolves into meaningless chaos. That absolute limit is known as the Planck length. Today we will explore the Planck length, the ultimate boundary of space and time, where our current laws of physics completely shatter. At a scale of roughly 1.6 multiplied by 10 to the power of negative 35 meters, our traditional understanding of geometry crumbles. At this unfathomably tiny distance, general relativity and quantum mechanics collide in a dramatic mathematical deadlock. If you try to build a microscope powerful enough to probe this subatomic realm, the sheer density of energy required would instantly collapse that region of space into a microscopic black hole. It is a frontier where physical location itself stops making sense, marking what many physicists consider the absolute limit of what can ever be measured in our universe. If you enjoy exploring these deep cosmic mysteries, feel free to leave a like and subscribe to the channel if you would like to see more content like this. Also, leave a comment down below letting us know where in the world and what time of day you are watching this right now. Now, let us dive into how we uncovered this invisible boundary. To truly understand why the Planck length represents such a profound threshold in physical reality, we first have to take a step back and examine how human beings have attempted to quantify the world around them throughout history. The story of measurement is fundamentally a story about our relationship with the universe. In the earliest stages of human civilization, measurement was entirely anthropocentric. Distance was intrinsically linked to the human body. Ancient societies relied on the length of a thumb to define an inch, the span of a hand to measure a horse, the length of a foot to measure land, or the distance from an elbow to the tip of the middle finger to mark out a cubit. While these units were undeniably convenient for building local shelters, trading agricultural goods, or crafting basic tools, they suffered from an inherent flaw. They were completely arbitrary and inherently inconsistent. A cubit defined by the forearm of a tall pharaoh differed significantly from a cubit defined by an average builder. As trade networks expanded, empires consolidated power, and early engineering projects grew in complexity, the need for standardized measurement became critical. Royal decrees attempted to enforce uniformity by declaring official physical reference standards, such as a specific bronze bar kept in a royal treasury, as the definitive unit of length for an entire nation. However, even these early standardized units remained fundamentally artificial. They depended entirely on specific, localized artifacts, geopolitical authority, or biological traits that held no universal significance outside of human culture. If a nation collapsed, or if its central physical reference standards were lost or damaged, the entire system of measurement risked losing its baseline. The major turning point in the history of measurement occurred during the Enlightenment, driven by the rapid growth of scientific inquiry and international trade. Scholars realized that scientific progress required a system of units that was independent of human anatomy and royal decree. This ambition culminated during the French Revolution with the creation of the metric system. The creators of the metric system sought to design a set of units that would be, as they famously declared, for all people for all time. Instead of relying on the body of a king, they turned to the planet Earth itself as their baseline reference. They defined the meter as 1/10,000,000th of the distance along a meridian line stretching from the North Pole to the equator, passing directly through Paris. To operationalize this definition, surveyors spent years meticulously measuring arcs of the Earth, eventually casting a physical metal bar made of platinum and iridium to serve as the definitive international prototype meter. For more than a century, this platinum iridium bar, stored in a climate-controlled vault in France, served as the ultimate standard of human distance. The metric system was a monumental leap forward for global science and engineering. Yet despite its brilliance and widespread adoption, theoretical physicists recognized that it still possessed a subtle, fundamental flaw. The metric system was still arbitrary. The circumference of the Earth is merely a historical accident of planetary formation. It carries no special significance in the broader context of cosmic physics. If a human scientist were to encounter an intelligent alien civilization on the opposite side of the galaxy, defining a meter based on the dimensions of a specific rocky planet in a distant star system would be completely meaningless to them. The meter remained a human construct, tailored to human planetary geography. This realization led 19th century physicists to ask a deeper question. Is it possible to construct a system of measurement that is not tied to human bodies, human artifacts, or even the specific planet we live on? Could there be a system of measurement derived entirely from the fundamental constants of nature itself, units that any advanced civilization anywhere in the universe would independently discover and recognize? Toward the end of the 19th century, the German physicist Max Planck provided the revolutionary answer to this question. Planck was working on the fundamental physics of thermodynamics and electromagnetic radiation when he noticed something extraordinary about the fundamental laws of nature. He realized that the universe possesses a set of fundamental constants that govern all physical phenomena. Among these are three overarching universal constants. First, there is the speed of light in a vacuum, denoted by the letter c. The speed of light is not just the speed at which light travels. It represents the ultimate speed limit of information, causality, and energy transfer throughout spacetime. Second, there is the gravitational constant, denoted by the capital letter G, which defines the intrinsic strength of the gravitational force pulling matter together across space. Third, there is Planck's constant, denoted by the lowercase letter h, or its reduced form h bar, which defines the scale at which quantum mechanical effects begin to dominate physical reality. Max Planck made a breathtaking observation. By mathematically combining these three absolute constants of nature, the speed of light, the gravitational constant, and Planck's constant, in specific algebraic arrangements, all human-defined units of mass, time, length, and temperature completely disappear from the equations. What emerges in their place is a pristine, objective set of measurement units built solely out of the raw parameters of the universe itself. Planck called these the natural units. Because natural units rely exclusively on the immutable properties of space, time, gravity, and quantum mechanics, they are entirely independent of human history, terrestrial geography, or biological evolution. They represent a universal language of measurement. If human scientists were ever to communicate with an extraterrestrial intelligence, both civilizations would share the exact same values for these fundamental natural units, because the underlying constants of the universe are identical everywhere in space and time. Among this set of universal parameters, which includes the Planck mass, the Planck time, and the Planck temperature, stands the Planck length. Max Planck calculated this fundamental unit of distance by combining his newly discovered quantum constant with the constants of gravity and light. When he evaluated the resulting formula, it yielded a distance so unbelievably minute that it seemed completely disconnected from any physical experience ever encountered by human beings. At the time of its mathematical derivation, the Planck length was viewed by many as an intriguing mathematical curiosity, a theoretical curiosity emerging from the intersection of constants, but without an obvious physical meaning in the everyday macroscopic world. Physicists of the late 19th century had no way of knowing that this tiny unit of length would eventually become the centerpiece of modern theoretical physics. What Max Planck had uncovered was not merely a convenient theoretical ruler for communicating with alien civilizations. Without fully realizing it, he had stumbled upon a fundamental scale where the continuous, smooth fabric of classical geometry breaks down entirely. The search for natural units had accidentally pointed humanity directly toward the absolute physical boundary of space itself, setting the stage for a profound revolution in our understanding of the universe. To understand how the Planck length transitioned from a simple mathematical combination of constants into the most mysterious boundary in modern physics, we must examine the crisis that birthed quantum mechanics at the dawn of the 20th century. In the late 1800s, classical physics was widely considered nearly complete. Isaac Newton's laws of motion and universal gravitation had successfully described the mechanics of the heavens and the movement of earthly objects for over 2 centuries. Meanwhile, James Clerk Maxwell had unified electricity, magnetism, and light into a single, elegant set of electromagnetic equations. According to Maxwell, light was a continuous wave moving smoothly through space, and energy was a continuous quantity that could be divided, absorbed, or emitted in any infinitely small amount imaginable. This smooth, continuous view of reality seemed indestructible until physicists turned their attention to a deceptively simple problem known as black-body radiation. A blackbody is an idealized physical object that absorbs all electromagnetic radiation that falls upon it. When heated, a blackbody emits light across a range of wavelengths, glowing red, then white, and then blue as its temperature increases. Physicists attempted to use the established laws of classical thermodynamics and Maxwell's wave theory of electromagnetism to predict the exact spectrum of light emitted by a hot blackbody at any given temperature. 2 prominent physicists, Lord Rayleigh and Sir James Jeans, derived a mathematical formula based entirely on classical principles. Their model worked reasonably well at long wavelengths, such as infrared light and radio waves. However, as the equations approached shorter wavelengths, specifically in the ultraviolet region of the spectrum, the classical model produced a catastrophic failure. Classical physics predicted that as the wavelength of emitted light approached zero, the energy radiated by the blackbody should approach infinity. According to classical theory, every time you turned on an oven or lit a candle, the object should immediately radiate an infinite amount of ultraviolet, X-ray, and gamma-ray energy, instantly vaporizing anything nearby. This complete collapse of classical theoretical physics became known as the ultraviolet catastrophe. It was a glaring, undeniable proof that something was fundamentally wrong with humanity's understanding of light, heat, and energy. The ultraviolet catastrophe exposed a deep flaw in the assumption that nature operates continuously at every scale. If energy could be emitted continuously at any arbitrarily tiny wavelength, the number of high-frequency vibrational modes inside a thermal cavity would be infinite, leading directly to the impossible, infinite energy predictions of the Rayleigh-Jeans law. In late 1900, Max Planck set out to resolve this deep contradiction. Planck was a deeply conservative physicist who favored classical thermodynamic principles, but he recognized that a radical mathematical intervention was required. To eliminate the infinite energy at short wavelengths, Planck made a daring theoretical assumption. He proposed that an atom absorbing or emitting electromagnetic energy does not do so in a smooth, continuous flow. Instead, he assumed that energy is exchanged only in discrete, indivisible packets, which he called quanta. According to Planck's quantum hypothesis, the energy contained within a single packet of radiation is directly proportional to the frequency of that light. Mathematically, this relationship was expressed through a strikingly simple formula. Energy equals a fundamental proportionality constant multiplied by the frequency of the radiation. That tiny proportionality constant came to be known as Planck's constant. Because high-frequency light, such as ultraviolet rays or X-rays, requires a much larger packet of energy than low-frequency radio waves, it is far more difficult for a thermal object to produce those high-energy quanta at ordinary temperatures. By restricting the emission of energy to these discrete packets, Planck's new formula suppressed the infinite ultraviolet radiation. The mathematical curve produced by Planck's formula matched experimental observations of black-body radiation with absolute perfection. Initially, even Max Planck himself viewed his concept of energy quantization as a clever mathematical trick, the temporary accounting tool rather than a literal description of physical reality. He hoped that future developments would restore the smooth, continuous wave nature of classical physics. However, in 1905, Albert Einstein extended Planck's idea to explain the photoelectric effect, demonstrating that light itself is not merely emitted in packets, but actually travels through space as localized packets of energy, which we now call photons. Energy was not a smooth fluid, it was granular. The discovery of Planck's constant fundamentally altered the trajectory of physics, marking the birth of quantum mechanics. It proved that at microscopic scales, the universe is not smooth or continuous, but quantized. Just as matter is made of discrete atoms rather than continuous fluid, energy is divided into irreducible units governed by Planck's constant. With the discovery of Planck's constant, physicists realized they possessed three foundational constants of nature, each governing a distinct pillar of physical reality. The speed of light, c, represents the limit of velocity and the bridge between space and time in relativity. The gravitational constant, g, dictates the strength of gravity and how mass bends space-time. And Planck's constant, h, defines the scale of quantum discreteness and uncertainty. Max Planck quickly noticed that combining these three immutable constants produced a unique set of fundamental units that did not rely on any human definitions. By performing dimensional analysis on these three constants, Planck derived a complete system of natural units. The Planck mass was defined as the square root of Planck's reduced constant multiplied by the speed of light and divided by the gravitational constant. This yielded a surprisingly large mass for a microscopic unit, roughly 20 micrograms, which is roughly equivalent to the mass of a flea egg. The Planck time was derived by dividing the Planck length by the speed of light, yielding a duration of approximately 5.4 multiplied by 10 to the power of negative 44 seconds. This represents the time it takes for light to travel a distance equal to 1 Planck length, marking the shortest meaningful interval of time in physics. The Planck temperature was calculated by combining the constants with Boltzmann's constant, yielding an astronomical value of roughly 1.4 multiplied by 10 to the power of 32 Kelvin. This represents the highest theoretical temperature possible, the thermal scale of the universe in the first instant following the Big Bang. And finally, at the core of this system was the Planck length. It was defined as the square root of Planck's reduced constant, multiplied by the gravitational constant and divided by the speed of light cubed. The result was a value of approximately 1.616 multiplied by 10 to the power of negative 35 meters. When Max Planck first published these natural units in 1899, he recognized their profound universal relevance, noting that they retain their meaning for all times and for all civilizations, even non-human ones. However, the physical reality of the Planck length remained unclear. Was it merely an arbitrary mathematical boundary where three constants intersected, or did it mark a physical brick wall in the geometry of space itself? As quantum mechanics developed throughout the 20th century, physicists slowly came to realize that the granular nature Planck had discovered in light and energy was not confined to electromagnetic radiation. The discovery of Planck's constant had laid the groundwork for a far more unsettling realization. If energy is quantized, and if gravity is linked to the geometry of space-time, then space itself cannot remain a smooth, continuous backdrop forever. The journey that began with solving the ultraviolet catastrophe was leading directly toward a profound breakdown in the definition of space at the Planck length. To truly appreciate the mystery of the Planck length, we must try to visualize its sheer, unimaginable scale. The human brain evolved to process distances encountered in everyday survival, meters, kilometers, or the height of a tree. When we venture far above or far below these everyday human scales, our natural intuition completely fails us. The Planck length measures approximately 1.616 multiplied by 10 to the power of negative 35 meters. Written out in standard decimal notation, it is a 0 followed by a decimal point, then 34 consecutive zeros, and finally the digits 1616. It is a number so vanishingly small that simply stating the exponent fails to convey the vast structural abyss separating our macroscopic world from this microscopic threshold. To bridge this conceptual gap, we must embark on a step-by-step journey of scale, zooming down into the physical sublevels of our universe, order of magnitude by order of magnitude. Imagine starting with a standard, everyday object, such as a single human hair or a grain of fine beach sand, measuring about 1/10 of a millimeter, or 10 to the power of negative 4 meters. To the naked human eye, this represents the lower boundary of visibility. If we zoom down by a factor of 100, reaching 10 to the power of -6 meters, or 1 micrometer, we enter the biological world of living cells. Here, red blood cells and microscopic bacteria swim through liquid environments. Zooming down another 2 orders of magnitude brings us to 10 to the power of -8 meters, the scale of single strands of human DNA and complex protein structures. Continuing further down to 10 to the power of -10 meters, or 1 angstrom, we hit the fundamental boundary of chemistry, the individual atom. An atom consists of a cloud of electrons orbiting a central nucleus. If you were to expand a single atom until it was the size of a massive professional sports stadium, the electron cloud would define the outer perimeter of the seating stands. Yet, if you search for the nucleus at the exact center of that stadium-sized atom, it would appear as nothing more than a tiny marble, or a single grain of rice, sitting at a scale of 10 to the power of -15 meters, or 1 femtometer. At 10 to the power of -15 meters, we reach the domain of nuclear physics. Here, protons and neutrons are packed tightly together inside the atomic nucleus. If we break open a proton and peer inside, we find point-like fundamental particles known as quarks, operating at scales around 10 to the power of -18 meters. This represents the absolute limit of modern experimental particle physics. The Large Hadron Collider, the most powerful particle accelerator ever constructed by humanity, smashes protons together at immense energies, allowing us to probe structure down to roughly 1,000th the size of a proton. Beyond this point, human technology cannot see. Yet, despite reaching the frontier of our most advanced instruments, we are nowhere near the Planck scale. The gap between the subatomic world of quarks and the Planck length is vastly larger than the gap between our everyday human world and the quark itself. To make this comparison undeniable, consider a dramatic thought experiment involving scaling up the universe. Imagine taking a single, tiny hydrogen atom, already invisible to the naked eye, and expanding it until it grew so enormous that its outer electron cloud matched the size of the entire observable universe, spanning 93 billion light-years across. In this utterly colossal expanded universe, where a single atom stretches across billions of galaxies, where would the Planck length fall? Even in an atom expanded to the size of the entire observable universe, the Planck length would still not be visible to the naked human eye. On this incomprehensible scale, the Planck length would equal the size of an ordinary, everyday tree on Earth. That is the incredible scale gap we are dealing with. The difference between an atom and the Planck length is identical to the difference between the entire observable universe and a single tree. Because this scale is so unfathomably small, it raises a fundamental physical question. Why can we not simply build a more powerful microscope to look at it? Why can we not use higher frequency light to zoom past the quark scale and take a direct photo of space at 10 to the power of -35 meters? The answer lies in the fundamental nature of light, wave mechanics, and optics. In classical optics, there is a strict rule known as the diffraction limit. To resolve an object or a physical feature of a certain size, the wavelength of the light you use must be equal to or smaller than the size of the object you wish to observe. If you attempt to view an object using a wavelength of light that is larger than the object itself, the wave simply bends around it, washing over the object without scattering off it to form a sharp image. To see smaller and smaller details, you are forced to use shorter and shorter wavelengths of light. Visible light has wavelengths between 400 and 700 nanometers, which is far too large to resolve individual atoms, let alone subatomic particles. To look inside an atom, physicists must abandon visible light and use high-energy radiation, such as X-rays or gamma rays, which possess vastly shorter wavelengths. However, quantum mechanics introduces a profound trade-off through the relationship discovered by Max Planck and Louis de Broglie. The wavelength of a photon is inversely proportional to its energy and momentum. Shortening the wavelength of light automatically increases the energy packed into each individual photon. A photon of visible light carries only a few electron volts of energy. A photon capable of probing the scale of an atomic nucleus carries millions of electron volts. A photon capable of probing a quark carries billions of electron volts. As you demand higher spatial resolution, you are forced to concentrate higher and higher densities of energy into smaller and smaller regions of space. This creates an insurmountable physical barrier as you approach the Planck scale. If you were to construct a hypothetical supermicroscope designed to shoot a photon with a wavelength equal to the Planck length, 1.6 multiplied by 10 to the power of negative 35 meters, that single photon would need to carry an astonishing amount of energy. It would require approximately 2 gigajoules of energy packed into a single quantum packet. 2 gigajoules is roughly equivalent to the chemical energy released by burning hundreds of liters of gasoline, or the electrical power consumed by a major city block over several seconds, all squeezed into a single subatomic particle. According to Albert Einstein's theory of general relativity, energy and mass are equivalent, and all forms of energy exert a gravitational pull. When you compress 2 gigajoules of energy into a volume of space defined by the Planck length, the localized energy density becomes so extreme that gravity takes over completely. The gravitational force of that hyperenergetic photon becomes so intense that space-time warps violently around it. Before that photon can scatter off your target and return to deliver an image, the region of space containing that energy collapses under its own immense gravity. It instantly forms a microscopic black hole. The boundary of this tiny black hole, its event horizon, expands to a size exactly equal to the Planck length, completely trapping the very light you sent in to make the observation. No information, no signal, and no reflected light can ever escape from behind that event horizon. If you attempt to overcome this barrier by increasing the energy even further to obtain a shorter wavelength and a clearer image, you only make the situation worse. Adding more energy to the photon increases the mass of the resulting micro-black hole, causing its event horizon to grow larger, not smaller. Instead of probing a finer scale, your higher energy microscope creates a larger black hole, swallowing an even bigger region of space and hiding even more detail from view. This represents a complete breakdown of the observational process. Light, which has been humanity's ultimate tool for exploring the cosmos, from distant galaxies down to subatomic particles, becomes completely useless at the Planck scale. The very act of attempting to look at the Planck length creates an optical shield made of collapsed space-time. Space itself actively prevents us from shining a light into its deepest foundations, marking an absolute observational wall beyond which traditional measurement stops making sense. To comprehend why the Planck scale represents such a profound roadblock in theoretical physics, we must analyze the fundamental conflict at the heart of modern science. Today, our understanding of the physical universe rests upon two exceptionally successful yet completely incompatible pillars. On one side stands Albert Einstein's general theory of relativity, which governs the grand macroscopic stage of the cosmos. On the other side stands quantum mechanics, which dictates the bizarre behavior of the subatomic realm. Both theories have passed every experimental test thrown at them over the past century with astonishing precision. Yet, when brought together at the Planck scale, they yield direct mathematical contradictions. To understand this deep structural conflict, we must first examine how each theory views the fabric of reality. General relativity is fundamentally a classical, deterministic, and geometric theory. Einstein reimagined space and time not as a static, passive stage upon which events unfold, but as a dynamic, four-dimensional fabric known as space-time. In this view, gravity is not a mysterious, invisible force pulling objects across distance, as Isaac Newton had suggested. Instead, gravity is the physical manifestation of geometry itself. Mass and energy tell space-time how to curve, and the curvature of space-time tells mass and energy how to move. A massive planet like Earth orbits the Sun simply because the immense mass of the Sun creates a smooth, gentle dip in the surrounding space-time fabric, and Earth is merely following the straightest possible path, called a geodesic, through that curved four-dimensional geometry. Crucially, general relativity relies on the assumption of absolute smoothness. The space-time manifold is assumed to be infinitely continuous, differentiable, and smooth at every conceivable scale. No matter how closely you zoom in on a region of space-time in general relativity, it remains perfectly flat and well-behaved, much like a smooth sheet of glass or the calm surface of an ocean viewed from high above. You can divide a light year into meters, millimeters, or fractions of a nanometer, and the underlying mathematical geometry remains completely intact and predictable. Everything in general relativity is continuous, elegant, and smooth. Quantum mechanics, however, paints a radically different picture of physical reality. At its core, quantum theory abandons the classical concepts of absolute determinism, smooth trajectories, and continuous quantities. Instead, it introduces intrinsic randomness, quantization, and probabilistic states. In the quantum realm, physical quantities like energy, angular momentum, and electric charge do not vary smoothly. They change in discrete jumps, or quanta. Central to this quantum worldview is the Heisenberg uncertainty principle, formulated by German physicist Werner Heisenberg. The uncertainty principle states that there are pairs of physical properties, such as position and momentum, or energy and time, that cannot be simultaneously measured with absolute precision. The more accurately you know the position of a subatomic particle, the less accurately you can know its momentum, and vice versa. This uncertainty is not a limitation of our technological instruments or experimental techniques. It is an intrinsic, built-in property of nature itself. At subatomic scales, a particle does not possess a single, well-defined location or trajectory. Instead, it exists as a cloud of probabilities described by a wave function. The act of measuring a particle forces the wave function to collapse, yielding a specific result governed by probability rather than absolute certainty. Furthermore, the uncertainty principle applies to energy and time. In quantum mechanics, energy can be borrowed from the vacuum for an extremely brief interval of time, provided that the borrowed energy is returned before the universe notices. The shorter the time interval you examine, the larger the quantum energy fluctuations can be. Because of this, the quantum vacuum is far from an empty, quiet void. It is a bustling sea of quantum fluctuations, where virtual particle-antiparticle pairs constantly pop into existence out of nothingness, interact briefly, and annihilate back into energy in fractions of a second. As long as physicists apply general relativity to massive objects over large distances, such as planets, stars, and galaxies, the smooth, continuous framework works flawlessly. And as long as physicists apply quantum mechanics to lightweight particles like electrons and photons over small distances, quantum theory delivers predictions of unmatched precision. For decades, physics operated comfortably by keeping these two theories strictly separated. However, the universe contains physical environments where immense mass and energy are squeezed into microscopic volumes. Under such extreme conditions, you cannot ignore gravity, nor can you ignore quantum mechanics. You are forced to apply both theories simultaneously to the exact same region of space. This is precisely where the conflict becomes catastrophic. When you attempt to apply the rules of quantum uncertainty to the smooth geometric fabric of space-time, the fundamental assumptions of both theories violently clash. General relativity demands that space-time remains smooth, continuous, and geometrically predictable at all scales. But quantum mechanics dictates that at extremely small distance scales and extremely short time intervals, energy fluctuations must become enormously violent. If energy fluctuates wildly on microscopic scales, and if Einstein's general relativity proves that energy bends space-time, then these violent quantum energy fluctuations must cause the surrounding space-time geometry to fluctuate wildly as well. At everyday macroscopic scales, these quantum gravitational ripples are so minuscule that space-time appears completely smooth and flat, just as a distant ocean looks perfectly calm from an airplane. However, as you zoom in closer and closer to the microscopic realm, the smooth geometric landscape begins to warp, twitch, and distort. At the scale of atoms and nuclei, these geometric fluctuations remain negligible. But as you push past the subatomic frontier and approach the Planck length, the energy density of these quantum fluctuations grows so extreme that the smooth geometric fabric of general relativity is completely torn apart. The smooth, predictable sheet of space-time envisioned by Einstein is invaded by the frantic, chaotic uncertainty of quantum mechanics. At this threshold, two of humanity's greatest scientific triumphs stand face to face in an unresolved impasse, signaling that our classical concepts of space and time are fundamentally incomplete. When theoretical physicists attempt to force general relativity and quantum mechanics into a single mathematical framework at the Planck scale, the resulting equations do not merely yield slight inaccuracies. They violently collapse, producing mathematical nonsense in the form of infinite values. In theoretical physics, when an equation outputs an infinite energy, an infinite probability, or an infinite curvature, it serves as a red flag indicating that the underlying model has completely broken down. The system is spitting back infinities because the assumptions built into the mathematical language itself no longer apply to physical reality at that extreme scale. To see how this mathematical breakdown occurs, we must examine how physicists historically unified quantum mechanics with other fundamental forces. In the mid-20th century, scientists successfully merged quantum mechanics with special relativity and James Clerk Maxwell's electromagnetism, creating quantum electrodynamics. Later, they incorporated the weak and strong nuclear forces, giving birth to the Standard Model of particle physics. The Standard Model views fundamental particles, such as electrons, quarks, and photons, as point-like entities with zero spatial volume. When calculating the interaction between two point particles, such as two electrons repelling each other by exchanging a virtual photon, physicists encountered a serious mathematical problem. Because the distance between two point-like particles can shrink to absolute zero, calculations involving distance in the denominator caused terms like electromagnetic potential or force to blow up to infinity. When calculating the total self-energy of an electron interacting with its own electromagnetic field, the equations consistently yielded infinite values. Physicists resolved this crisis in quantum field theory through a sophisticated mathematical procedure called renormalization. Renormalization allows scientists to manage and isolate these infinite terms. By redefining physical parameters like mass and charge at a specific reference scale and subtracting the infinite baseline contributions, the infinities cancel out precisely. What remains are finite, ultra-precise numerical predictions that match laboratory measurements down to 12 decimal places. Every fundamental force in the Standard Model, electromagnetism, the weak nuclear force, and the strong nuclear force, turned out to be renormalizable. However, when physicists applied this exact same renormalization technique to gravity, the system completely failed. Gravity is fundamentally different from the other forces. In quantum electrodynamics, the strength of the electromagnetic interaction is governed by a dimensionless coupling constant. But in quantum gravity, the coupling constant is related to Newton's gravitational constant, which carries physical dimensions of length and mass. Because the gravitational force couples directly to energy and momentum rather than a fixed charge, every time a graviton, the hypothetical quantum particle of gravity, interacts with another particle, it interacts with the energy of that particle. But quantum fluctuations at extremely short distance scales carry huge amounts of energy. As you calculate gravitational interactions at smaller and smaller scales, virtual particle loops demand higher and higher energy inputs. In quantum electrodynamics, a finite set of counterterms is sufficient to absorb all the infinities. In quantum gravity, each increase in energy scale requires adding brand new counterterms to fix new levels of infinities. To calculate even a simple gravitational interaction at ultra-short distances, you would need an infinite number of parameters, requiring an infinite number of experiments to calibrate the theory. A theory that requires infinite inputs to predict a single outcome loses all predictive power. Quantum gravity derived from standard field theory is fundamentally non-renormalizable. This non-renormalizability is not merely an abstract mathematical inconvenience. It reflects a deep physical contradiction when applying point-like quantum mechanics to general relativity at the Planck length. In classical general relativity, space-time is a continuous, smooth manifold. In standard quantum field theory, field interactions occur at specific mathematical points in space-time. But if you try to define a precise mathematical point at coordinates down to 10 to the power of -35 meters, the The uncertainty principle demands that the momentum and energy uncertainty in that infinitesimal volume must approach infinity. According to Einstein's field equations, energy density dictates the curvature of spacetime. If the energy density inside an infinitesimal Planck scale volume approaches infinity, the predicted spacetime curvature at that point also approaches infinity. A region with infinite curvature is, by definition, a gravitational singularity. Instead of describing a well-behaved background where subatomic particles interact, standard quantum gravity predicts that every single point in space should constantly collapse into an infinite density of microscopic singularities. The geometry of space-time would be torn into infinite, isolated black hole horizon boundaries, completely destroying the smooth background required for particles to travel or exist. Probability calculations for simple physical processes, such as two gravitons scattering off each other, yield probabilities greater than 100%, or infinite probability, which is physically impossible. This mathematical catastrophe reveals that the concept of a point-like particle and the concept of a smooth space-time continuum are fundamentally incompatible. You cannot simply take the equations of general relativity, convert the gravitational field into a quantum field of point-like gravitons, and expect the math to work at subatomic distances. At scales larger than the Planck length, this naive approach works fine as an effective field theory, because the quantum fluctuations of spacetime are tiny enough to be ignored. But as soon as your scale shrinks toward 1.6 multiplied by 10 to the power of negative 35 meters, the approximations explode into infinite values. The emergence of these unavoidable infinities serves as definitive proof that physics has hit a hard conceptual wall. Space-time cannot be infinitely smooth, nor can physical interactions take place at true zero-dimensional points. The failure of renormalization at the Planck scale tells us that our macroscopic concepts of space and time are merely emergent approximations. Just as the smooth, continuous flow of liquid water breaks down when you examine individual water molecules, the smooth geometric continuum of space-time breaks down into mathematical nonsense when forced into scales smaller than the Planck length. To eliminate these infinities, theoretical physics must replace the smooth space-time manifold with a radically new geometric language. To visualize what actually replaces the smooth fabric of space-time at the microscopic limit, we must turn to a revolutionary concept introduced in 1955 by the theoretical physicist John Archibald Wheeler. Wheeler was a visionary who helped shape modern relativity and quantum mechanics, coining famous terms like black hole and wormhole. He realized that if you took the principles of quantum uncertainty and applied them directly to the geometry of spacetime, the peaceful, continuous picture of the universe would undergo a violent transformation at ultra-small scales. Wheeler called this dynamic, turbulent state quantum foam. To grasp the concept of quantum foam, consider an everyday analogy involving a smooth, glassy body of water viewed from an airplane flying thousands of feet in the air. From that high altitude, the surface of the ocean appears completely flat, static, and continuous. It looks like an unbroken sheet of blue glass extending all the way to the horizon. You could easily describe its geometry using simple, smooth curves. However, as your plane descends closer and closer to the water, that illusion of smoothness begins to vanish. At an altitude of a few hundred feet, you start to see rolling swells and large waves. Descending further down to the surface, right where the water meets the air, the smooth geometry vanishes entirely. You no longer see a flat plane. Instead, you see a chaotic, frothing mess of breaking waves, splashing droplets, bursting bubbles, and chaotic foam. At the microscopic boundary, the liquid is violent, turbulent, and constantly changing its local topology. Wheeler argued that space-time behaves in precisely the same way. At our macroscopic human scale, space feels completely smooth, rigid, and continuous. We can move through it smoothly in three spatial dimensions without feeling any friction, bumps, or resistance from the vacuum. Even at the atomic scale, space-time retains enough geometric smoothness that quantum equations can treat the background as a stable, fixed stage. However, as you zoom down past the scale of molecules, past individual atoms, past atomic nuclei, and past fundamental quarks, the smooth geometry of general relativity begins to warp and twitch under the pressure of quantum uncertainty. When you finally reach the Planck scale, at distances around 10 to the power of negative 35 meters and time intervals around 10 to the power of negative 44 seconds, the quiet geometry of space complicated dissolves. At the Planck length, space-time is no longer a passive flat sheet. It becomes a violent, boiling sea of quantum activity. At this scale, the energy fluctuations dictated by Heisenberg's uncertainty principle become so massive that they distort the local geometry of space in extreme ways. Tiny, short-lived warps, twists, and microscopic distortions appear and vanish in fractions of a Planck time unit. In classical physics, geometry obeys strict topological rules. A flat piece of paper stays flat unless you physically tear it. A sphere remains a sphere, and a donut maintains its central hole. The topology of a space determines how points are connected to one another. But inside Wheeler's quantum foam, the very topology of space-time becomes dynamic and probabilistic. Space is no longer statically connected. At the Planck scale, space-time can tear, restitch itself, and form temporary topological bridges. Microscopic wormholes, tiny tunnels connecting distant regions of space-time, can spontaneously pop into existence, persist for a fraction of a Planck time unit, and snap shut. Tiny handles, loops, and microscopic bubble-like structures form continuously. Geometry loses its smooth, fixed nature and becomes a fluctuating, probabilistic foam of geometry. This chaotic turbulence is intimately linked to the concept of the quantum vacuum. In classical physics, a vacuum is defined as absolute empty space, a region where all matter, light, and energy have been completely removed. It is a total void. In quantum mechanics, however, a true static void is physically impossible. Because of the energy-time uncertainty principle, the energy level of any quantum field cannot remain fixed at absolute zero with complete certainty. A field with zero energy would have a precisely known value and zero momentum, violating quantum uncertainty. Therefore, even in a pristine vacuum devoid of all matter, quantum fields possess a minimum non-zero energy state known as zero-point energy. This zero-point energy causes the quantum vacuum to constantly boil with activity. Virtual particles, pairs of matter and antimatter particles, such as electrons and positrons, or virtual photons, spontaneously create themselves out of empty space. These virtual particles borrow energy directly from the vacuum, exist for an unimaginably brief moment, and then collide with each other to annihilate back into pure energy, returning their borrowed energy to the vacuum before any macroscopic law of conservation can be violated. At ordinary subatomic scales, these virtual particle creation events occur against a relatively stable background of space-time. But as you zoom down to the Planck length, the energy density of these virtual particle fluctuations reaches unbelievable heights. The virtual particles popping in and out of existence carry so much mass energy within such a tiny volume that their individual gravitational fields react violently with the surrounding space-time fabric itself. At the Planck scale, you can no longer separate the particles from the space they occupy. The virtual particles alter the geometry of space-time, and the fluctuating geometry of space-time drives the creation of more virtual energy. Space and matter merge into a single, interconnected, chaotic, dynamic system. One of the most unsettling consequences of quantum foam is what happens to our fundamental concepts of distance, direction, and cause and effect. In our macroscopic world, order relies on clear geometric relationships. Point A is a specific distance away from point B, and to get from A to B, you must travel along a continuous line passing through every intermediate point in between. Furthermore, cause precedes effect, because signals travel forward in time through space at speeds no faster than the speed of light. Inside the Planck-scale quantum foam, these familiar rules break down completely. Because geometry is fluctuating wildly, and temporary wormholes are constantly opening and closing, the concept of a shortest path between 2 points loses its meaning. Point A might briefly connect directly to point B through a Planck-scale topological bridge, bypassing all intermediate space, only for that bridge to collapse a moment later. Distance ceases to be a smooth, fixed number. If you attempt to measure the distance between 2 points at the Planck scale, the quantum uncertainty in the geometry itself causes the measurement to fluctuate wildly. The distance is not a fixed quantity, but a blurred probability distribution. Even the arrow of time experiences a complete breakdown within the quantum foam. In general relativity, time is tightly bound to space as part of a smooth four-dimensional manifold. But at the Planck length, the chaotic geometry can warp space-time so severely that the distinction between past, present, and future becomes blurred. Local light cones, the mathematical structures that define which regions of space-time can causally influence another, can tilt, twist, and point in random directions. At the Planck scale, time loses its smooth, forward-flowing directionality and becomes a chaotic, multidirectional variable. This means that at the most fundamental level of reality, concepts like cause and effect, before and after, or left and right, are not fundamental properties of the universe. They are emergent features that only appear when you zoom out to much larger scales, just as the temperature or pressure of a gas only emerges when you aggregate billions of individual, bouncing molecules. When we look at the universe through a macroscopic lens, we experience a calm, well-behaved cosmos governed by predictable geometry and smooth trajectories. But that calm is a macroscopic illusion built upon a raging, chaotic foundation. Beneath the quiet surface of empty space lies a submicroscopic ocean of quantum foam, where space and time continuously boil, twist, tear, and rebuild themselves at a rate of 10 to the power of 44 times every single second. The Planck length is the exact frontier where this underlying chaos completely overwhelms the smooth illusion of geometric space. To probe the fundamental nature of physical reality at increasingly smaller scales, experimental physics has historically relied on a straightforward strategy: build large accelerators and smash particles together at higher energies. This strategy is rooted in the de Broglie wavelength relationship, which dictates that a particle's spatial resolution is inversely proportional to its momentum and energy. To resolve details at a scale 10 times smaller, you must increase the probing particle's energy by a factor of 10. For over a century, this brute force approach powered every major breakthrough in particle physics, taking us from the discovery of the atomic nucleus to the observation of the Higgs boson. However, when this fundamental principle is pushed to its ultimate theoretical extreme, the attempt to probe the Planck length, it runs headfirst into a profound physical paradox. The very strategy that enables subatomic measurement triggers a mechanism that completely destroys our ability to observe anything at all. This phenomenon is known as the Planck energy paradox, and it demonstrates that the Planck length is not merely an engineering milestone that human technology has failed to reach, but an absolute physical wall built into the architecture of space-time. To understand how this paradox operates, consider the physics of observation. In order to measure an object or confirm the existence of a feature at a specific point in space, you must send a probe, such as a photon, electron, or proton, to interact with that region and return information to a detector. To distinguish 2 points separated by a specific distance, the probe's wavelength must be equal to or smaller than that distance. If the distance you want to measure is the Planck length, roughly 1.6 multiplied by 10 to the power of negative 35 meters, the probing particle must have a Compton wavelength that matches or falls below this scale. According to quantum mechanics, the energy carried by a particle is inversely proportional to its Compton wavelength. A photon with a wavelength on the scale of the Planck length requires an energy concentration of approximately 2 gigajoules, or roughly 1.22 multiplied by 10 to the power of 19 giga-electron volts. This value is known as the Planck energy. To put this energy scale in perspective, the Large Hadron Collider at CERN accelerates protons to a collision energy of approximately 13 trillion electron volts, or 13 tera-electron volts. The Planck energy is more than 16 orders of magnitude beyond the reach of human technology. It represents a single subatomic particle carrying the kinetic energy of a macroscopic object, such as a heavy automobile traveling at highway speeds. The energy paradox emerges when we analyze what happens when this staggering quantity of energy is localized within a microscopic volume of space. Albert Einstein's special theory of relativity established that mass and energy are equivalent, expressed through the famous relation where energy equals mass multiplied by the speed of light squared. Energy exerts a gravitational pull just as rest mass does. In classical general relativity, if a sufficient quantity of mass or energy is concentrated inside a region bounded by its Schwarzschild radius, the localized gravitational field becomes so immense that space-time curves inward completely. The escape velocity within that boundary exceeds the speed of light, and the region collapses into a black hole. The Schwarzschild radius for any given mass or energy is directly proportional to that energy. If you pack more energy into a region, its Schwarzschild radius grows larger. Now consider the dual scaling behavior that occurs as you try to probe smaller and smaller distances. On one hand, quantum mechanics dictates that as you target a smaller spatial scale, the required probing energy increases, making the Compton wavelength shrink. On the other hand, general relativity dictates that as the probing energy increases, the Schwarzschild radius of that localized energy expands. At ordinary subatomic scales, the Compton wavelength of a particle is far larger than its corresponding Schwarzschild radius. For an electron, the Compton wavelength is millions of times larger than the distance at which its localized mass energy could form an event horizon, meaning quantum wave effects completely dominate over gravitational collapse. As you increase the energy of your probe to target smaller distances, the Compton wavelength shrinks toward the microscopic scale, while the hypothetical Schwarzschild radius creeps upward from zero. These two fundamental curves, the shrinking quantum Compton wavelength and the expanding relativistic Schwarzschild radius, intersect at one precise physical location in the universe. That intersection occurs exactly at the Planck length, corresponding to the Planck energy. When you pack the Planck energy into a region of space equal to the Planck length, the Schwarzschild radius of that concentrated energy becomes exactly equal to the Planck length itself. The energy required to observe space at the Planck scale creates a microscopic black hole whose event horizon completely encloses the region you are trying to measure. This leads directly to a profound observational breakdown. Suppose you attempt to bypass this barrier by building a hypothetical supercollider capable of reaching energies beyond the Planck energy. You hope that by packing 3 times or 10 times the Planck energy into a collision, you will produce a particle with a wavelength 3 or 10 times smaller than the Planck length, allowing you to peak inside the Planck scale. However, the laws of gravity intervene with absolute authority. If you supply 10 times the Planck energy, the localized energy density instantly collapses space into a micro black hole. But because the energy is 10 times higher, the resulting black hole is not smaller. Its Schwarzschild radius expands by a factor of 10. Instead of probing a distance 10 times smaller than the Planck length, your higher energy collision creates an event horizon 10 times larger than the Planck length, hiding a far bigger volume of space behind an opaque horizon boundary. If you continue to scale up the energy of your accelerator to probe finer details, you do not gain higher spatial resolution. You simply produce larger, more massive black holes that swallow increasingly large regions of space-time. The event horizon expands, completely trapping all photons, particles, and information within its interior. No signal, light ray, or scattered probe can ever escape from behind a black hole horizon to deliver data back to your external detectors. This counterintuitive behavior completely inverts our traditional understanding of particle physics. At energies well below the Planck scale, higher energy means smaller distances and higher spatial resolution. But once you reach the Planck scale, higher energy means larger black holes and lower spatial resolution. The Planck length represents the absolute minimum achievable distance scale in the universe, a physical turning point where the relationship between energy and spatial resolution reverses direction. Furthermore, these micro black holes created at the Planck energy are governed by the strange laws of quantum thermodynamics discovered by Stephen Hawking. Correct to Hawking's theory of black hole radiation, black holes emit thermal radiation and lose mass over time, with a temperature that is inversely proportional to their mass. A massive astronomical black hole radiates at an imperceptibly tiny fraction of a degree above absolute zero and survives for unfathomable eons. However, A microscopic black hole with a mass near the Planck mass possesses a Hawking temperature equal to the astronomical Planck temperature, roughly 10 to the power of 32 Kelvin. Because its temperature is so extreme, a Planck-scale micro-black hole explodes almost instantly, evaporating its entire mass in a burst of high-energy particles within a duration equal to the Planck time, roughly 5 multiplied by 10 to the power of negative 44 seconds. The time required for the micro-black hole to form and completely evaporate is identical to the time it would take light to travel across the Planck length. The measurement process destroys itself before any meaningful signal can be generated, processed, or recorded. This operational reality reveals a fundamental truth about space-time. The limitation is not a temporary hurdle created by the technological weakness of human engineering, nor is it a problem that can be solved by building larger particle colliders or more sensitive sensors. It is a fundamental law of nature, enforced by the mutual interaction of quantum mechanics and general relativity. The physical act of operational definition requires that a concept must be measurable, at least in principle, through a physical experiment. If an experiment to measure a distance smaller than the Planck length inevitably creates a black hole that prevents the extraction of any information from that region, then the concept of a distance smaller than the Planck length lacks operational physical meaning. Space-time actively defends its own privacy. Beyond the Planck length, the continuous framework of geometric distance evaporates, proving that our classical notion of space as an infinitely divisible stage is nothing more than a macroscopic illusion. The emergence of unavoidable mathematical infinities at the Planck scale forced theoretical physicists to search for a new paradigm, a framework capable of harmonizing gravity with quantum mechanics without triggering the collapse of space-time into endless singularities. For decades, the primary candidate leading this effort has been string theory. String theory offers an extraordinarily elegant resolution to the mathematical breakdowns of quantum gravity, but to achieve this, it demands a radical overhaul of our most fundamental assumptions regarding the building blocks of matter and the dimensionality of space itself. In standard quantum field theory, which forms the bedrock of the standard model of particle physics, fundamental particles such as electrons, quarks, and neutrinos are treated as zero-dimensional point particles. They are modeled as mathematical points with no internal structure, no width, no depth, and zero physical volume. While this point particle approximation works with remarkable precision at macroscopic and subatomic scales, it is the direct source of the mathematical catastrophe at the Planck length. When two zero-dimensional point particles interact, the physical distance between them can approach absolute zero. In the classical formulas for gravity and electromagnetism, force is inversely proportional to the square of the distance. As the distance between two zero-dimensional points shrinks to zero, the denominator of the equation vanishes, causing physical quantities such as energy density, gravitational field strength, and probability amplitudes to blow up to infinity. Standard quantum field theory manages these infinities through renormalization, but as we have seen, quantum gravity resists renormalization because graviton interactions grow stronger with increasing energy, generating an infinite series of unmanageable infinities. String theory resolves this crisis by making a single, revolutionary conceptual shift. It eliminates the zero-dimensional point particle entirely. According to string theory, if you could zoom in far past the reach of modern particle accelerators, down to the scale of the Planck length, you would discover that fundamental particles are not mathematical points at all. Instead, they are tiny one-dimensional vibrating filaments of energy, known as fundamental strings. A string can be open, possessing two distinct endpoints, or closed, forming a continuous loop. Just as a single violin string can vibrate at different frequencies to produce different musical notes, a C, an E, or a G, a fundamental physical string can vibrate in different modes. The specific vibrational pattern, frequency, and energy of the string dictate the observed macroscopic properties of the particle. One vibrational mode manifests as an electron, with its specific mass, electric charge, and spin. A different vibrational mode of the exact same underlying string manifests as an up quark, a photon, or a gluon. Matter and force are unified under a single musical metaphor. The universe is a vast symphony played on vibrating fundamental strings. Crucially, string theory naturally predicts the existence of a particle whose vibrational mode corresponds to a massless spin-2 particle. This particle is none other than the graviton, the long-sought quantum carrier of the gravitational force. In standard quantum field theory, physicists had to artificially insert gravity into quantum mechanics, which consistently triggered mathematical failure. In string theory, gravity cannot be turned off. It is an unavoidable organic consequence of closed string vibration. The physical key to how string theory eliminates the infinities at the Planck scale lies directly in the one-dimensional extension of the string. Because a string has a finite physical size, typically estimated to be on the order of the Planck length, roughly 10 to the power of negative 35 meters, it replaces zero-dimensional point interactions with smooth, extended interaction surfaces. Consider what happens when two point particles interact in standard quantum field theory. They meet at a sharp, infinitely precise point in spacetime, creating a zero-dimensional vertex. It is this sharp vertex that causes the mathematical equations to divide by zero and spit back infinite values. But when two closed strings interact, they do not meet at a single point. Instead, two closed strings approach each other, touch, and merge into a single intermediate string, which later splits apart into two outgoing strings. If you draw this string interaction in a spacetime diagram, it does not look like a collection of sharp lines meeting at a jagged point. Instead, it forms a perfectly smooth two-dimensional surface that resembles a pair of pants or a branching pipe. Because the interaction is smeared out over a smooth two-dimensional surface, there is no single, localized point in spacetime where the interaction takes place. Different observers moving at different velocities will disagree on where the strings actually merged. By smearing the interaction across the spatial extent of the string, the sharp, zero-dimensional vertex is completely eliminated. Without zero-dimensional vertices, the equations never divide by zero, and the mathematical infinities that plagued quantum gravity simply disappear. String theory is inherently finite. However, replacing point particles with vibrating strings introduces a fascinating consequence for our understanding of distance and the Planck length. In a universe composed of strings, the Planck length ceases to be a barrier where space collapses into chaos. Instead, it acts as the absolute minimum meaningful spatial scale in nature. To understand why, consider what happens when you attempt to probe distances using strings instead of point particles. When you boost the energy of a point particle, its quantum wavelength shrinks, allowing you to probe finer and finer spatial details indefinitely until gravity triggers a black hole. But when you pour energy into a string, something very different happens. At low energies, increasing the energy speeds up the string and shrinks its effective quantum wavelength. But as the energy approaches the Planck energy, the extra energy no longer shrinks the probe. Instead, the energy goes into stretching the string itself, causing it to expand in size. When you try to probe distances smaller than the Planck length by pumping more energy into a string collision, the strings absorb the energy and stretch into long, chaotic, extended loops. Instead of probing smaller scales, the probe expands, covering a larger region of space. This leads to a remarkable duality in string theory, known as target space duality, or T-duality. T-duality proves mathematically that a universe in which extraspatial dimensions are curled up into a circle of radius r is physically identical and completely indistinguishable from a universe where those dimensions are curled up into a circle of radius 1 divided by r, measured in units of the Planck length. If you attempt to shrink a dimension down below the Planck length, the physical behavior of the strings smoothly mirrors itself back toward large distances. A radius of 1/10 the Planck length exhibits the exact same physical states, scattering amplitudes, and energy spectra as a radius 10 times the Planck length. The Planck length acts as a cosmic mirror. Distances smaller than the Planck length do not exist as distinct physical realities. They are merely mathematically equivalent dual representations of distances larger than the Planck length. While strings solve the problem of infinities and establish a minimum length scale, they demand a heavy price from our intuitive picture of the cosmos, the existence of extraspatial dimensions. When physicists derived the quantum mathematics governing vibrating strings, they discovered a severe anomaly. In standard four-dimensional spacetime, 3 spatial dimensions plus 1 time dimension, the quantum probabilities for string vibrations failed to conserve probability, yielding negative probabilities and mathematical nonsense. To restore mathematical consistency and eliminate these quantum anomalies, the equations of string theory yielded a strict requirement. Strings must vibrate in a spacetime possessing more than 4 dimensions. In superstring theory, which incorporates supersymmetry between bosons and fermions, the universe must possess exactly 10 dimensions, 9 spatial dimensions and 1 time dimension. This requirement immediately raises an obvious question. If the universe possesses 9 spatial dimensions, why do we only experience 3? Where are the remaining 6 spatial dimensions hidden? The answer offered by string theory lies in the concept of compactification. Imagine looking at a long, thin garden hose from a distance of several hundred yards. From that far away, the hose appears as a one-dimensional line. You can describe the position of an ant on that hose using a single coordinate, how far left or right the ant is along the length of the hose. However, if you step closer and examine the hose through a magnifying glass, you discover that the hose has a second hidden dimension, a small circular cross-section wrapping around its circumference. The ant can move left and right along the long dimension, but it can also walk around the tiny circular dimension. String theory proposes that our universe operates under the exact same principle. The 3 spatial dimensions we experience every day, up, down, left, right, and forward, backward, are vast expanded dimensions that stretched out during the Big Bang, spanning billions of light years. The remaining 6 spatial dimensions, however, never expanded. They remained curled up or compactified into hyper-microscopic geometric shapes attached to every single point in our 4-dimensional spacetime. What do these hidden, compactified dimensions look like? Mathematicians and physicists discovered that to preserve specific physical symmetries required for quantum mechanics and particle physics, these 6 extra dimensions must be folded into complex geometric manifolds known as Calabi-Yau shapes. A Calabi-Yau manifold is a 6-dimensional geometric structure composed of intersecting complex loops, holes, and handles. Crucially, the physical size of these curled-up Calabi-Yau shapes is predicted to be on the order of the Planck length. At every single location in your room, inside your body, and across the far reaches of intergalactic space, a 6-dimensional Calabi-Yau geometry is folded tightly at a scale of 10 to the power of -35 meters. These hidden Planck-scale geometries are not merely passive mathematical decorations. The precise geometric shape, topology, and arrangement of holes within the Calabi-Yau manifold directly dictate the vibrational modes of the strings passing through them. The way a string vibrates as it winds around the microscopic loops of a Calabi-Yau shape determines the fundamental constants of our world, the masses of elementary particles, the strength of the electromagnetic force, and the fine structure constant. The fundamental laws of physics experienced in our macroscopic world are dictated by the microscopic geometry of space at the Planck scale. Through vibrating strings and compactified Calabi-Yau dimensions, string theory provides a compelling vision for resolving the crisis of the Planck length. It tames the mathematical infinities of quantum gravity by replacing zero-dimensional points with finite strings, and it sets the Planck length as an absolute physical mirror, below which smaller distances lose all meaning. Yet string theory remains a theoretical framework under active development, facing significant challenges in experimental verification, setting the stage for alternative approaches to the nature of spacetime. While string theory resolves the crisis at the Planck scale by introducing vibrating strings moving through a higher dimensional background, a powerful alternative theoretical framework takes a fundamentally different approach. That alternative is loop quantum gravity. While string theory attempts a unified theory of all fundamental forces in particles, loop quantum gravity focuses squarely on a more specific, profound goal: quantization of general relativity itself. Loop quantum gravity proposes that we do not need extra spatial dimensions, supersymmetry, or exotic new matter to understand quantum spacetime. Instead, We simply need to apply the lessons of quantum mechanics directly to the fabric of space-time, without assuming any background stage at all. To appreciate the conceptual leap of loop quantum gravity, consider the concept of background independence. In almost every branch of traditional physics, from classical Newtonian mechanics to Maxwell's electrodynamics, quantum mechanics, and even string theory, equations are constructed on a fixed, pre-existing spatial backdrop. Physicists assume a background stage, set up a coordinate system, and then describe how particles, fields, or strings move across that stage. However, Albert Einstein's general theory of relativity taught us that spacetime is not a static, passive stage. Spacetime is itself a dynamic physical field, the gravitational field. In general relativity, there is no fixed background stage. The geometry of spacetime dynamically interacts with matter and energy. Therefore, a true quantum theory of gravity must be background independent. It must not describe quantum particles moving through space. It must describe the quantum structure of space itself. Space cannot be the stage on which the play occurs. Space must be built out of the quantum actors themselves. This background-independent approach was pioneered in the late 1980s and 1990s by theoretical physicists Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, among others. Ashtekar reformulated Einstein's equations of general relativity using a new set of mathematical variables, now known as Ashtekar variables, which expressed gravitational geometry in a language similar to the gauge theories used in particle physics. When Rovelli and Smolin applied standard quantum operator mathematics to these new gravitational variables, they discovered something extraordinary. The geometry of space itself becomes quantized. In classical general relativity, space is continuous, smooth, and infinitely divisible. You can take a volume of space, such as the inside of a box, and divide it into halves, quarters, or billionths of a cubic millimeter indefinitely. But loop quantum gravity proves that, at the quantum level, space is not a continuous fluid. Just as matter is composed of discrete atoms, and light is composed of discrete photons, space itself is composed of discrete, indivisible quantum building blocks. Geometry is atomic. The fundamental building blocks of space in loop quantum gravity are derived directly from mathematical structures called spin networks. A spin network, first proposed by mathematician Roger Penrose and later integrated into loop quantum gravity by Rovelli and Smolin, is a mathematical graph consisting of discrete nodes connected by one-dimensional lines or edges. It is crucial to understand that these spin network graphs do not exist in space. They are not physical threads floating inside an empty room. Instead, the spin network is space. The nodes and edges of the spin network create spatial relationships through their purely topological connections. In this quantum picture, a single node within a spin network represents a discrete quantum grain of volume, a localized elementary chunk of spatial volume. The edges or lines connecting one node to another represent the quantum boundaries separating adjacent grains of volume. When an edge intersects a boundary surface between two nodes, it confers a discrete quantum unit of surface area to that boundary. When physicists calculate the mathematical operators corresponding to area and volume in loop quantum gravity, they obtain a discrete spectrum of eigenvalues, precisely analogous to how the energy levels of an electron in a hydrogen atom are restricted to discrete quantum values. Space-time geometry cannot take on arbitrary continuous values. It is restricted to specific, quantized numerical steps. And what dictates the scale of these fundamental quantum steps? The answer, once again, is the Planck length. In loop quantum gravity, the smallest possible non-zero unit of surface area, the absolute minimum area eigenvalue, is directly proportional to the square of the Planck length, roughly 10 to the power of negative 70 square meters. There is no such thing as a physical surface with an area smaller than this Planck area. Similarly, the smallest possible non-zero unit of spatial volume, a single node of a spin network, is on the order of the cube of the Planck length, or the Planck volume, approximately 10 to the power of negative 105 cubic meters. This discovery provides a stunningly intuitive physical picture of reality at the Planck scale. If you could zoom in on the room around you, past the smooth illusion of everyday distance, down past atoms and quarks, you would eventually hit the absolute atomic fabric of space. You would not see a continuous backdrop or a chaotic boiling liquid. You would see a vast, interconnected, three-dimensional web of spin network nodes and edges. Space is a dense mesh of quantized geometric threads, woven together at the scale of the Planck length. Because space is built out of these discrete Planck scale units, the concept of a smooth continuum completely dissolves. Between two adjacent nodes of a spin network, there is no spatial gap, no empty void, and no intermediate space waiting to be measured. The question of what lies between two fundamental grains of space is physically meaningless, in the exact same way that asking what lies between two individual atoms of gold inside a gold bar is meaningless. Space does not exist between the nodes. Space is the network of nodes. This atomicity of space completely eliminates the mathematical infinities that plagued classical quantum gravity. In standard calculations, infinities arise because integrations allow distances to approach zero. But in loop quantum gravity, zero distance does not exist. The distance between two adjacent spatial nodes cannot shrink smoothly to zero. It is bounded from below by the discrete Planck length scale. Because there is a hard lower limit to spatial resolution, equations never divide by zero, and energy densities can never blow up to infinity. When time is incorporated into loop quantum gravity, the dynamic evolution of spin networks creates a four-dimensional quantum structure known as a spin foam. A spin foam represents the quantum history of evolving spin network. As time advances in discrete quantum steps, governed by the Planck time, roughly 10 to the power of negative 44 seconds, nodes and edges within the spin network can undergo topological transformations. A single node can split into two nodes, increasing local volume. Two nodes can merge into one, or connections between nodes can rewire themselves. These discrete quantum transitions in spin foam geometry replace the smooth time evolution described by classical relativity. Time is not a smooth, continuous river flowing quietly in the background. Time is a tick-tock sequence of quantum geometric reconfigurations occurring at the rate of one Planck time interval per step. In loop quantum gravity, both space and time lose their continuous nature and become fully quantized digital processes operating at the Planck scale. This granular picture of space-time yields a remarkable consequence for our understanding of extreme physical phenomena, such as the Big Bang and the interiors of black holes. In classical general relativity, tracing the expansion of the universe backward in time leads inevitably to an initial gravitational singularity, a zero volume point of infinite density and infinite temperature at time zero. In loop quantum cosmology, the application of loop quantum gravity to the universe as a whole, that initial singularity completely disappears. As the early universe contracts backward in time, matter and energy are compressed into an increasingly small volume. In classical physics, this volume shrinks to absolute zero. But in loop quantum gravity, space cannot be squeezed smaller than the Planck volume per quantum node. When the density of matter and energy approaches the Planck scale, roughly 1 Planck mass per Planck volume, the quantized fabric of space develops a powerful repulsive quantum force. The atomic grains of space resist further compression, acting like an incompressible quantum fluid. Instead of collapsing into an infinitely dense point singularity, the universe hits a physical density ceiling, stops contracting, and bounces outward. This phenomenon is known as the Big Bounce. According to loop quantum cosmology, our Big Bang was not the absolute beginning of space and time out of nothingness, but rather a violent quantum bounce transitioning from a previous contracting cosmic phase into our current expanding phase. The Planck length acts as a cosmic spring, preventing the universe from ever destroying itself in a point singularity. A similar mechanism resolves the singularity at the heart of black holes. In classical general relativity, a massive star collapsing under its own gravity forms an event horizon and continues collapsing until all its mass is concentrated at a single, zero-dimensional point singularity. In loop quantum gravity, matter falling inside a black hole cannot compress past the Planck scale density limit. Instead of an infinite singularity, the core of the black hole forms an ultra-dense star-like object composed of Planck-scale space-time grains, sometimes called a Planck star. Over time, quantum tunneling effects allow this Planck star to bounce back outward, transforming the black hole into a white hole and releasing all trapped energy and information back into the universe. The Planck scale serves as an absolute cosmic shield against the formation of true mathematical infinities anywhere in nature. By replacing the smooth geometric manifold of Einstein with a discrete background-independent web of spin networks, loop quantum gravity offers a compelling, self-consistent picture of physical reality. It demonstrates that the Planck length is not merely a theoretical curiosity or an observational boundary. It is the fundamental physical size of a single atom of space. Space is not an infinite void waiting to be filled, but an endless woven tapestry of quantum geometry. To fully appreciate how the Planck scale governs the structural boundaries of our universe, we must examine two extreme cosmic frontiers where classical physics breaks down entirely: the interior singularities of black holes and the very first moment of creation during the Big Bang. In standard cosmology and general relativity, both of these states represent mathematical dead ends, points where the curvature of space-time and the density of matter reach absolute infinity. However, when we apply the physical scales defined by the Planck units, these terrifying infinities evaporate, revealing a physical limit governed by the interplay of quantum mechanics and gravity. In classical general relativity, a black hole is not merely a region of heavy mass with a strong gravitational pull. It is an inevitable journey toward an infinite boundary. Once a massive star exhausts its nuclear fuel and collapses under its own gravity, its inward momentum crushes all internal thermal pressure. If the mass exceeds the Tolman-Oppenheimer-Volkoff limit, no known physical force can halt the collapse. The star shrinks past its event horizon, trapping light and matter within a point of no return. Classical general relativity predicts that inside the event horizon, the trajectory of all collapsing matter inevitably leads to a single location, a zero-dimensional point of infinite density, infinite temperature, and infinite space-time curvature, known as a gravitational singularity. At this mathematical point, the laws of classical physics completely cease to operate. The equations spit back infinite values, rendering time and space entirely meaningless. However, the existence of a true singularity is widely viewed by theoretical physicists as a signature of an incomplete theory. Infinities do not exist in physical reality. They are mathematical warnings indicating that a theory has been extrapolated beyond its valid domain. When quantum effects are incorporated into the collapse process, the Planck scale intervenes to prevent this breakdown. As matter collapses inside a black hole, it is squeezed into smaller and smaller volumes. When the volume containing the collapsing mass shrinks down to the scale of the Planck length, roughly 1.6 multiplied by 10 to the power of negative 35 meters, the spatial density of that matter approaches the Planck density, roughly 10 to the power of 96 kilograms per cubic meter. At this extreme density, quantum mechanical uncertainty and quantum pressure generate an immense outward resistance. According to various quantum gravity models, space-time itself cannot be compressed past the Planck volume. Instead of collapsing into a zero-dimensional point of infinite density, the falling matter hits a fundamental quantum ceiling at the Planck scale. The singularity is replaced by an ultra-dense core where space-time curvature reaches a maximum finite value governed by the Planck length. The Planck length acts as a physical flaw, preventing the absolute destruction of matter and geometry into mathematical non-existence. A similar, equally profound application of the Planck scale occurs when we look back toward the absolute beginning of our universe. Modern observational cosmology, anchored by measurements of the cosmic microwave background radiation and the expansion of distant galaxies, allows us to trace the history of the cosmos backward in time. As we rewind the cosmic clock, the universe becomes smaller, denser, and hotter. If we extrapolate Einstein's equations of general relativity all the way back to time zero, we encounter another classical singularity, the Big Bang singularity. Classical cosmology predicts that 13.8 billion years ago, the entire observable universe, containing hundreds of billions of galaxies, was squeezed into a point of zero volume and infinite density, marking the absolute creation of space and time out of nothingness. Yet, just as with black hole interiors, this classical prediction fails because it ignores quantum mechanics. In the early universe, as the cosmic volume contracts past atomic and subatomic scales, quantum gravitational effects become the dominant force in nature. This brings us to the earliest possible epoch in cosmic history, known as the Planck epoch. The Planck epoch corresponds to the time interval between time zero and 1 Planck time unit, approximately 5.4 multiplied by 10 to the power of negative 44 seconds after the expansion began. During this fleeting fraction of a second, the entire observable universe was contained within a spatial region no larger than a single Planck length across. At this scale, the energy density was so astronomical that the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were unified into a single, symmetrical, fundamental superforce. Gravity was not a weak force acting across empty space. It was equal in strength to the subatomic nuclear forces. Space and time were not a smooth, expanding backdrop. They were a violently fluctuating quantum foam. Because our current understanding of physics relies on treating gravity separately from the other three forces, modern science cannot describe what actually occurred during the Planck epoch. To write down a physical law for a universe smaller than the Planck length and younger than the Planck time requires a fully tested, verified theory of quantum gravity. At time intervals shorter than 10 to the power of negative 44 seconds, our macroscopic concepts of before and after, as well as cosmic clock time, completely break down. When the universe expanded past the age of 1 Planck time unit, it crossed the Planck boundary. The scale of the observable cosmos expanded beyond the Planck length, energy densities dropped below the Planck density, and the temperature cooled below the Planck temperature of 10 to the power of 32 Kelvin. At this precise moment, gravity broke away from the other fundamental forces. Space-time settled from a violent quantum foam into a smooth, expanding geometric fabric, and classical general relativity began to provide an accurate description of cosmic expansion. The existence of the Planck epoch fundamentally changes our philosophical understanding of the Big Bang. Rather than marking a moment where the universe emerged from a point of absolute mathematical zero, the Planck time represents a cosmic horizon, a wall past which our current physical language cannot peer. Whether the universe began at the Planck scale through a quantum fluctuation, or whether it underwent a bounce from a previously contracting universe, as suggested by loop quantum cosmology, the Planck length sets the scale for the ultimate origin story of our cosmos. It marks the boundary where the universe transitions from an unpredictable quantum state into the structured, expanding spacetime we inhabit today. Both in the heart of black holes and at the birth of the cosmos, the Planck scale stands as nature's absolute barrier against the void of infinity. To fully comprehend how the Planck scale governs the ultimate boundaries of physical reality, we must examine a profound realization that emerged from the intersection of black hole thermodynamics, quantum information theory, and quantum gravity, the holographic principle. For centuries, classical physics treated space as a three-dimensional container capable of holding an arbitrary amount of matter and information. It was assumed that if you doubled the volume of a box, you doubled its capacity to store data. However, the study of black holes at the Planck scale revealed a staggering counter-reality. The maximum amount of information that can be packed into any region of space is not proportional to its three-dimensional volume, but to its two-dimensional surface area, measured strictly in fundamental units of the Planck area. This radical insight began in the 1970s with groundbreaking work by Jacob Bekenstein and Stephen Hawking. Bekenstein asked a deceptively simple question. What happens to the second law of thermodynamics when you throw a hot cup of tea into a black hole? The second law states that the total entropy, a measure of disorder and microscopic quantum information, of an isolated system must always increase or remain constant. It can never decrease. If a black hole possessed zero entropy, tossing matter into it would permanently destroy the information contained within that matter, violating the second law of thermodynamics and creating a profound crisis in physics. Bekenstein proposed that black holes must possess intrinsic entropy, and that this entropy must grow whenever a black hole swallows mass. Stephen Hawking initially resisted this idea because anything possessing entropy must also possess a temperature and radiate thermal energy, which classical black holes were believed impossible of doing. However, when Hawking incorporated quantum field theory into the curved spacetime surrounding a black hole, he discovered that black holes do indeed emit quantum radiation, now known as Hawking radiation. When Hawking calculated the precise mathematical formula for black hole entropy, he uncovered a breathtaking relationship. The entropy of a black hole is directly proportional to the surface area of its two-dimensional event horizon, divided by 4 times the square of the Planck length. Mathematically, this is expressed as 1/4 of the event horizon area measured in Planck units. A single unit of Planck area, roughly 10 to the power of -70 square meters, corresponds precisely to 1 fundamental unit, or bit, of quantum information. This formula, known as the Bekenstein-Hawking entropy formula, holds profound consequences for our understanding of space and matter. In standard thermodynamics, the maximum information capacity of a 3-dimensional region of space scales with its volume. If you fill a computer hard drive or a cubic meter of gas with data, the number of possible microscopic arrangements scales with the number of atoms contained inside that 3-dimensional volume. However, black hole thermodynamics proves that black holes represent the ultimate maximum entropy state for any given region of space. If you attempt to pack more matter or information into a 3-dimensional volume than its equivalent black hole capacity, the energy density becomes so extreme that the region collapses into a black hole. The boundary of that black hole expands to enclose the region, and its total information capacity becomes strictly limited by the surface area of its surrounding event horizon. This absolute upper bound on the maximum entropy contained within any spatial region is known as the Bekenstein bound. The realization that information is bounded by area rather than volume led theoretical physicists Gerard 't Hooft and Leonard Susskind to formulate the holographic principle in the 1990s. The holographic principle proposes that our everyday experience of a 3-dimensional physical world may be an emergent illusion. Just as a 2-dimensional hologram on a credit card uses a flat surface to project a 3-dimensional visual image when light shines through it, the physical processes occurring within a 3-dimensional volume of space-time can be entirely encoded on a distant 2-dimensional boundary surface wrapped around that volume. In this holographic worldview, the fundamental pixels of physical reality are not 0-dimensional mathematical points in 3-dimensional space. Instead, the universe is built out of 2-dimensional quantum pixels, each possessing an area equal to 1 Planck area. Every fundamental decision in nature, every quantum bit or qubit of data representing the presence or absence of a particle, a spin state or a gravitational curvature, is recorded on a Planck scale boundary pixel. The 3-dimensional reality we observe around us, containing planets, stars, and human beings, is merely a holographic projection generated from the quantum information stored on this 2-dimensional Planck scale boundary. In 1997, theoretical physicist Juan Maldacena provided a rigorous mathematical proof of the holographic principle through a breakthrough known as the ADS-CFT correspondence, or anti-de Sitter conformal field theory correspondence. Maldacena demonstrated that a 5-dimensional universe containing quantum gravity, an anti-de Sitter space, is mathematically identical and completely equivalent to a 4-dimensional quantum field theory operating on its outer boundary without gravity. Everything happening inside the higher dimensional gravitational bulk can be translated line by line into the language of subatomic quantum interactions on the lower dimensional boundary. The holographic principle completely reframes our understanding of the Planck length. The Planck length is not just a microscopic ruler for measuring small distances in 3 dimensions. It is the physical resolution limit of the cosmic hologram. It defines the size of an individual pixel on the boundary screen of reality. Trying to probe a distance smaller than the Planck length is mathematically equivalent to trying to zoom in on a digital television screen past the size of an individual display pixel. There is no finer detail to observe because the fundamental hardware encoding the information cannot record a fraction of a Planck pixel. Furthermore, This information-centric perspective provides a revolutionary new angle on the nature of space-time itself. Theoretical physicists like Eric Verlinde have suggested that gravity and space-time are not fundamental forces or building blocks of nature at all. Instead, space-time may be an emergent property derived from the quantum entanglement of Planck-scale information pixels on a boundary surface, much like how fluid pressure and temperature emerge from the collective motion of microscopic molecules. If you disentangle the quantum bits on the boundary, the three-dimensional geometry inside collapses and vanishes. Space-time is literally woven together by quantum information organized at the scale of the Planck length. By demonstrating that information capacity is bounded by the Planck area, the holographic principle proves that the universe is fundamentally digital at its deepest foundation. The Planck length stands as the ultimate pixel size of space, time, and information, anchoring the vast three-dimensional cosmos to a microscopic surface of quantum code. While theoretical frameworks like string theory, loop quantum gravity, and the holographic principle offer fascinating descriptions of space at the Planck scale, physics is ultimately an empirical science. A hypothesis, no matter how mathematically elegant, must be tested against physical reality. This presents an immense challenge when dealing with the Planck length. As established earlier, building a traditional particle accelerator capable of probing distances on the order of 10 to the power of -35 meters would require a machine the size of the Milky Way galaxy. Direct observational probing at the Planck energy remains far beyond human technological capabilities. However, experimental physicists have developed ingenious methods to circumvent this brute force barrier. Rather than attempting to build accelerators that reach the Planck scale directly, scientists search for tiny, cumulative observational signatures left behind by Planck-scale quantum geometry as light travels across cosmic distances, or as ultra-sensitive instruments measure microscopic spatial displacements. These indirect observational techniques allow us to test predictions about the quantum structure of space using existing technology. One of the primary experimental avenues involves testing the foundation of Albert Einstein's special theory of relativity, Lorentz invariance. A core postulate of relativity is Lorentz symmetry, which states that the laws of physics, including the speed of light in a vacuum, are identical for all inertial observers, regardless of their velocity or the energy of the light. According to classical general relativity, space-time is perfectly continuous and smooth, meaning a high-energy photon and a low-energy photon travel through empty space at the exact same speed, denoted by the constant c. However, many theories of quantum gravity suggest that if spacetime is granular, discrete, or fluctuating at the Planck length, this classical smoothness breaks down. In these models, empty space acts almost like a physical medium, a dispersive material similar to glass or water. As light travels through space, its quantum wave senses the underlying Planck scale texture. Because higher energy photons have shorter wavelengths, they interact more strongly with the submicroscopic geometry than low-energy, long-wavelength photons. This predicted phenomenon is known as Lorentz invariance violation, or quantum gravity dispersion. If Lorentz symmetry is broken or deformed at the Planck scale, photons of different energies emitted simultaneously from a distant cosmic source should travel through space at slightly different velocities. For a single light-year, the time difference between a high-energy gamma-ray photon and a low-energy optical photon would be so imperceptibly tiny that no clock on Earth could measure it. To make this infinitesimal time delay observable, physicists use the cosmos itself as a gigantic natural laboratory. They look across billions of light-years at some of the most energetic explosions in the universe, gamma-ray bursts. A gamma-ray burst is an intense flare of high-energy electromagnetic radiation caused by the collapse of a massive star into a black hole or the collision of two neutron stars. These events release huge torrents of radiation across a wide spectrum of energies within fractions of a second, originating from galaxies billions of light-years away from Earth. As these photons travel across the universe for billions of years, any tiny velocity difference caused by Planck-scale space-time granularity accumulates over time. By the time the radiation reaches Earth, the minute difference in travel speed scales up into a measurable time delay of milliseconds or seconds between high-energy gamma rays and lower-energy X-rays or visible light. Astronomers use space-based observatories, such as NASA's Fermi Gamma Ray Space Telescope, to detect these cosmic events and measure the arrival times of individual photons. In 2009, Fermi recorded a powerful explosion designated Gamma Ray Burst 080916C, located over 12 billion light-years away. Among the incoming signal was a 31 giga-electron-volt gamma-ray photon that arrived within 9 seconds of low-energy photons emitted at the same instant. If the Planck length created a large dispersion effect, that high-energy photon should have experienced a significant time delay after traveling across 12 billion light-years of quantum foam. The fact that high-energy and low-energy photons arrived almost simultaneously placed tight upper limits on Lorentz invariance violation. These observations demonstrated that if space-time is discrete or dispersive, the scale of that discreteness must be smaller than the Planck length, effectively ruling out several simplified models of quantum spacetime. A second experimental frontier involves searching for quantum gravity noise using laser interferometry. A laser interferometer, such as those used in the Laser Interferometer Gravitational Wave Observatory, or LIGO, splits a laser beam into 2 perpendicular arms, bounces the beams off mirrors positioned miles away, and recombines them at a detector. If a passing gravitational wave stretches one arm while compressing the other by a fraction of an atomic nucleus width, the interference pattern of the recombined laser light shifts, revealing the spatial displacement. Physicists realized that these ultra-sensitive instruments might also detect the intrinsic quantum fluctuations of space-time itself. If space is composed of quantum foam, or Planck-scale pixels, the positions of the mirrors in an interferometer should not remain perfectly fixed at subatomic levels. The geometry itself should jitter, creating a faint, persistent background noise in the interference signal, known as holographic noise or quantum geometric noise. In the early 2010s, scientists at the Fermi National Accelerator Laboratory built a specialized instrument called the holometer to test this prediction. The holometer consisted of 2 high-precision 40-meter laser interferometers operating side by side. It was specifically designed to detect correlated spatial jitter at frequencies of megahertz, searching for signatures of Planck-scale spatial quantization predicted by certain formulations of the holographic principle. After years of data collection and statistical analysis, the holometer experiment yielded a null result. It found no evidence of holographic spatial jitter down to the sensitivity levels where quantum geometric noise was predicted to appear. The mirrors remained locked in position within the bounds of standard quantum optics, placing strong constraints on specific holographic models that predicted macroscopic spatial fluctuations derived from the Planck scale. Additional observational tests focus on astronomical measurements of distant blazars, optical coherence of distant stars, and precision laboratory experiments involving cold atom interferometry and optomechanical resonators. Modern experimental setups attempt to create macroscopic quantum superposition states in heavy microscopic objects, testing whether gravity induces quantum state decoherence at scales linked to the Planck mass and length. While these experimental efforts have not yet provided direct, definitive proof of a specific theory of quantum gravity, they demonstrate a profound milestone in modern science. The Planck length is no longer a purely philosophical construct inaccessible to human inquiry. Through clever observational techniques that leverage cosmic distances, extreme astronomical energy releases, and hypersensitive laser measurement, experimental physics is actively probing the boundaries of spacetime. Every null result refines our models, carving away invalid hypotheses and narrowing the search area. We are systematically placing upper limits on quantum spacetime fluctuations, forcing theoretical physics to build frameworks that respect both quantum mechanics and observational reality. The quest to measure the Planck length proves that humanity's search for the ultimate foundation of space is shifting from mathematical speculation into the realm of testable, empirical science. The journey to the Planck length brings humanity face to face with the ultimate horizon of scientific inquiry. Standing at a scale of roughly 1.6 multiplied by 10 to the power of -35 meters, we do not merely discover a small unit of distance, we uncover a fundamental boundary where our language, mathematics, and physical intuition lose their meaning. The Planck length represents much more than a technical hurdle for experimental physics. It marks a profound philosophical transition in how we conceptualize reality itself, forcing us to re-examine the relationship between human thought, physical measurement, and the objective cosmos. For centuries, science operated under the unspoken assumption that nature is infinitely divisible and continuously accessible. Classical physics imagined space as an infinite, smooth canvas, waiting to be mapped out to arbitrary precision. The discovery of the Planck length shattered this reductionist dream. Whether space dissolves into Wheeler's chaotic quantum foam, resolves into the woven spin networks of loop quantum gravity, mirrors itself through string duality, or encodes its three-dimensional reality on two-dimensional holographic boundary pixels, one conclusion stands firm. Space is not continuous. The smooth geometry of our everyday macroscopic world is an emergent approximation, a high-level illusion born from the statistical aggregation of microscopic quantum structures. This realization exposes a deep epistemological limit. Human concepts of length, duration, location, cause and effect evolved to navigate a macroscopic world governed by classical mechanics. When we force these words into the realm of the Planck scale, they fail. Asking what lies inside a Planck volume or what happened before a Planck time interval is like asking what color a single electron is or what lies north of the North Pole. The questions themselves are flawed because they rely on macroscopic concepts that do not exist at that fundamental level. The Planck scale defines the operational limit of our current physical language. Yet this limit is not a symbol of failure, but a testament to the power of human intellect. Bound to a small rocky planet on the edge of an ordinary galaxy, armed only with mathematics and logical deduction, humanity has successfully deduced the absolute physical flaw of space and time. We have identified the precise point where quantum mechanics and general relativity clash, defining the exact frontier where a true unified theory must operate. As we look toward the future of physics, the Planck length stands as a beacon guiding our search for a deeper framework. It reminds us that reality at its core may not be made of physical matter or geometric space, but of pure quantum information. The Planck scale challenges us to abandon comfortable macroscopic assumptions and build a new scientific language capable of describing a universe where space and time are not the stage, but the product of a deeper quantum reality. In reaching the absolute boundary of space, we have not hit an end to knowledge, but the doorway to a truly fundamental understanding of the cosmos.